Set up equipment. Place the tester on the surface. Adjust the leveling screw until the bubble spirit level is perfectly centered. Then, raise the pendulum arm to the horizontal lock position. Release the arm without it touching the ground. The pointer should swing to 0. If not, adjust the friction ring until it registers 0. Setting the contact patch. Lower the pendulum arm head so that the rubber slider barely touches the surface. The rubber slider should remain in contact with the surface. The test swing. Ensure the surface is free and loose grit or stone. Skid resistance is almost tested, wet and simulated the worst case scenarios. Spray the contact area and the rubber slider with clean water. To execute, bring the arm to the horizontal release position. Press the release button. As the arm swings up to the other side, catch it on the return to prevent it from striking the surface again. Repetition and consistency. Perform at least 3 swings on the same spot, rewetting the surface before every single swing. The readings should be consistent. If they vary widely, check the debris or instrument leveling issue. Calculate the mean of the 3 readings. For the discussion, a dry condition recorded a mean BPN of 50, which was used to calculate skid number of 38 at 0 speed and 29.45 at 60 km per hour. These values indicate a moderate level of skid resistance, suggesting that the pavement provides adequate tire grip under dry condition. However, the reduction in SN at higher speed demonstrates that skid resistance decreased as vehicle speed increased due to reduced tire pavement contact efficiency. The wet condition recorded a higher mean VPN of 53.53, resulting in a skid number of 42.60 at 0 speed and 33 at 60 km per hour. The higher BPN and SN values indicate better skid resistance compared to the dry condition, suggesting that the pavement surface maintains good friction even when wet. This improved skid resistance can help reduce the risk of vehicle skidding and enhance driving safety, although the SN still decreases in increasing speed. The difference may be influenced by experimental factors such as surface condition, equipment variability, or limited sample size. In practice, dry surface generally provide higher skid resistance than wet surface. Therefore, additional testing with more repetitions is recommended to improve the reliability of the result.
Firstly, select a dry pavement area. Avoid areas with visible cracking. And then we use a brush to remove all loose debris, dust and aggregate from the test area. The void must be clear to receive the sand. Thirdly, we measure 25 ml of sand using the measuring cylinder and pour the sand through the funnel. Next, pour the measured volume of sand into a small cone in the center of the clean test area. Using the spreader disc, apply light pressure and move in a slow circular motion into a thin surface. Then, measure the diameter 3 times in a perpendicular line direction using ruler. The surface is clean and the sand reclaimed. After that, add water to the test area to stimulate high moisture conditions. And then we repeat step 3 to 7 and then we analyze the recorded data. Moving on to the discussion of our sand patch test results, we compared the measurement taken on both a dry rough surface and a wet rough surface to evaluate the pavement's macro texture. First, let's look at the dry surface. we recorded a mean texture depth, or MTD, of 1.15 mm. This safely surpasses the standard safety baseline of 0.5 mm. What this data tells us is that the pavement has a robust macro texture. This depth is highly capable of efficiently dispersing surface water, which is vital for lowering skidding and drifting risks and ensuring strong tire grip for passing vehicles. Next, we examine the wet surface, which yields an MTD of 1.79 mm. While this number technically clears the 0.5 mm minimum, this result is actually invalid. The presence of water on the surface forces the standard sand particle to bind together. Because of this clumping, the sand creates a much narrower spread, averaging only 13.33 cm in diameter, which results exaggerated and inaccurate MTD value. Therefore, executing this test is on a damp road compromises the results, as the sand is simply unable to properly fill the pavement's natural texture. In summary, while both tests showed depth values above the minimum requirement, only the dry test offers a legitimate assessment of the road's friction capabilities. Our valid dry result proved that the pavement has a sufficient structural profile. This confirms that it is an optimal, secure choice for high-speed sections where reliable braking and vehicle control are absolutely critical.
First, we need to pour 200 ml of water into the outflow meter. Second, we will open the valve and start the stopwatch to record the time. Third, we have to run the test for 3 times to get the average data. Finally, let's discuss our finding. The experimental data demonstrate a high level of consistency, with outflow time recorded at 9.2 seconds, 9.3 seconds, and 9.1 seconds. This minimal variance implies that the sample has a uniform surface texture and that the testing procedure was highly repeatable. However, minor discrepancy in the timing can be attributed to human reaction time when operating the stopwatch. Additionally, when conducting this test, factors such as lateral water leakage under the sealing ring or residual moisture trapped in the pavement from previous trial could marginally affect the exact flow time. Overall, the tag cluster around 9.21 means confirm the reliability of the results.
In conclusion, the skid resistance test recorded an average value of 50 under dry conditions and 53.33 under wet conditions. The results demonstrate that the pavement provides adequate friction in both conditions, with the wet surface exhibiting slightly higher resistance, likely due to the interaction between the testing equipment and the moist surface texture. Next, the sand patch test have an average diameter of 14.45 cm for the dry surface and 13.33 cm for the wet surface. The smaller diameter obtained under wet conditions indicates a slightly greater surface macro texture depth, which enhance water drainage and reduce the likelihood of water film formation on the pavement. The surface drainage test produced an average outflow time of 9.21 seconds, indicating that the pavement surface is capable of draining water effectively within a relatively short period. Effective drainage minimizes water accumulation, thereby lowering the risk of hydroplaning and contributing to safer driving conditions during rainfall. The three tests indicates that the pavement possesses satisfactory surface texture, effective drainage capability, and adequate skid resistance. These characteristics contribute to improved pavement performance, enhance driver safety, and reduce accident risks, particularly during wet weather conditions.